The periodic table itself. Let's take a look at this. If you take a look at that periodic table that is on the wall or in your sheet, it's kind of an odd shape, right? It's not a square, really. It's not organized in a way that you might have organized it yourself, but there is a lot of meaning in how we manipulate the periodic table. And so when we look at the periodic table, I'm going to refer to it in several ways. Now, there are a couple important pieces about it, and so what I want to do is identify ways that we look at it. First, the period, the ones that go across. There are different periods, and we can refer to them. We don't refer to the periods as often, but we really do talk quite often about groups. They're the vertical up and downs. The way we organize the periodic table is to take advantage of having elements in groups, because the groups are going to specify how they are similar. In terms of knowing something about the periodic table, here's what the groups allow us to do. We can learn a property about an entire group of elements instead of having to memorize individual things. So if I know about the group, I know about all of those elements together. So it makes the information extraction off the periodic table much easier. So we're going to even name the groups in just a bit. When I take a look at the periodic table, there is an important stair step. And if you see it's a little bit highlighted, I will make it a little bit more. Right here, right there, right here, right there. This stair step is a dividing line. And what it divides is a group or a type of elements, and probably is not, that's not cool, that are indicated right here. These are called the non-metals. And a group of elements that are called, down here, that are called the metals. Okay. Do you see something that doesn't fit in any of those groups? Well, yeah, hydrogen should actually be a non-metal. It's kind of oddball. Those green ones? All right. They're sandwiched right between the metals and the non-metals. All right. They are confused. They can't make up their mind. We call them metalloids. Okay. The metalloids are easiest to identify because they're the elements that actually touch the stair step, with the exception of two. That one right there. What is Al? Aluminum. An aluminum can is definitely a metal. Okay. And then PO, polonium, is definitely a metal. Those are the only two that touch the line that are not metalloids. Everything else that touches the line is a metalloid. All right. Now, if I say metal, what are properties about metals that are the same about metals? What do you think when I say a metal, what do you picture, what would you describe them as being? What is it? Iron is a metal, and when you look at iron, what are some things about iron? They're solids, and most of them are solids. What else? Yeah, a lot of metals are really shiny. And if you buff them up, all metals become shiny if you buff them up. So they can have that particular property. If you hit a metal with a hammer, do they shatter? No, they can bend, right? And the fact that they can bend, it's called malleable, all right, that property. If I take a piece of metal and I stretch it, does it break? Before it actually breaks, it really gets pulled into a what? Very thin thing called a wire. and the term is metals are ductile. If I took a rod of metal and I shoved it into an electrical socket, what might happen to me? Yeah, I'd probably go to the hospital, I might have a new hairdo, and I might even die, okay? I'm dying a lot today. And so what does that metal do to the electricity? We call it conducts electricity. So did anybody ever roasted a marshmallow on a hanger, a wire hanger, right? And so you pull out that marshmallow, what don't you want to touch? That metal, right? Because if it sticks in the fire, it gets hot. And so it conducts also heat. And so has anybody ever cooked with a iron skillet? Yeah, good. It does really good cooking. But you do this once. You pick it up with your hand just once, okay? Because that handle is going to be just as hot as the pan itself because it conducts that heat. All right, so there's a lot of things about metals that are the same. Non-metals are kind of the opposite. Where metals conduct, non-metals are non-conductors, okay? Or we call them insulators. And so to pick up that metal, iron skillet, what do you use? A pot holder, right? Something that is cotton usually. That cotton is a non-metal and it prevents heat from going through and it doesn't conduct. Or if I use carbon, which is a non-metal, I put it around the wire to keep it from conducting electricity outside the wire, allows the wire to be moved around, and because if a wire touches something, it's going to conduct the electricity. But surrounding it by a non-metal will insulate it. The other things about non-metals are kind of generalized. There's not a lot that makes them up. They tend to, if solids, they tend to shatter if you hit them, like a ceramic plate. They have a whole bunch of different other properties, but they're a lot more various, but they are insulators and they usually shatter if they're solids. Metalloids can't make up their mind, okay? They might be shiny just like a metal, but if you hit it with a hammer, it shatters just like a plate. In terms of conductivity, they are called semiconductors. They only conduct every so often. Now there's a whole industry that has built up around it and a whole valley that is named after it. Silicon Valley is, and the semiconductors are what makes computer chips possible because they only conduct electricity in pulses and we can manipulate that to make computers work. And so there are quite a lot of difference between metals and non-metals, and then the metalloids are in the middle. All right? If we look at the periodic table on the wall, there's some more information that you can find. One, if an element is solid black, okay, then at room temperatures, normal temperatures and normal pressures, the element is a solid. Okay. If it is a red element, do you know what it is? It's a gas. Okay. If the element is blue, do you know what that is? It's a liquid. Do we have a lot of liquids? No, we don't have a lot of liquids on the periodic table. Now, it's only liquid at normal pressures and normal temperatures. If you heat something up, I can take a solid and melt it into a liquid, or I can take a liquid and turn it into a gas. But these are reference points. At normal pressures and temperatures, if you're going to find it on Earth, it's going to be in these states. There's one more thing, and they're kind of weird. You can either call them white or outlined. What are those elements? They are man-made or radioactive to the point that they don't stick around long enough. They're the ones that tend to have on them the weights that are in parentheses, meaning that they don't last long enough for us to even measure them well. Okay? And so The white ones are completely made up or synthesized in laboratories. And so if I take a look at 97, that element has BK, that's not Burger King. That element is berkelium. I wonder where they made that element. University of Berkeley, University of California, Berkeley. Okay. CF is californium, made in a UC system. ES, number 99, is einsteinium. Now, Einstein didn't make that one, but he was famous enough that they named it after him. And so, NO, nobelium. Have you ever heard of someone called Nobel? What is he famous for? Prizes. His first prize that he created was the Peace Prize. Do you know why he created the Peace Prize? It was absolutely out of guilt. Okay? He was a chemist, and he made one compound that just sold all over the world. The compound that he made was trinitrotoluene, known as TNT. And it was used as a weapon against his wishes. And he earned and became very rich on something that he thought was horrible in terms of how people used his invention and what he discovered. And so what he did is he took his fortune and created first the Peace Prize and then created other prizes to innovate towards creation and peace. And so number 117, Tennessee. It is an element that was created at Oak Ridge National Labs, and so we just, this was actually just named, the last few ones were just named probably a couple months ago and had official names. And so those are elements that are just created in a laboratory, and they're not something that we can use to make compounds. A lot more, these are made in physics experiments. All right, the symbols that you need to know the names of. The first 36, like I said, and then a list of other ones. We used one yesterday called U. What was that one? Uranium. AG, do you know what that one is? That one is silver. AU is gold. HG is mercury. If you look at mercury, mercury is a metal, but it's a liquid metal. That's very unusual. Okay, and some others that we'll interact with. Okay, here's a listing. We already identified difference between metals and nonmetals. Just wanted to make sure that you had a listing and you didn't miss anything. Now, many of the elements will behave very similarly, and so we give them names of groups. And so the first group, if you take a look on the periodic table, it says group up there, number 1, is called the alkali metals. Hydrogen is a special element. It kind of doesn't fit anywhere. It will sometimes react like an alkali metal, so we put it there. Sometimes it reacts totally different. The group number 17 on the periodic table are called the halogens. This one we refer to quite a lot. Group number 2 is called the alkaline earth metals. They all behave very similarly. And group number 18 at the end are called the noble gases. Sometimes you find them called the inert gases. Okay? If there were elements at Disneyland on the periodic table, this would be them. They're on the happiest place on earth. Okay? The noble gases don't react with anything. They are perfectly balanced and happy. And we're going to refer to the noble gases because they have a perfect arrangement of how the electrons live around nuclei. Okay? Now we get really creative. The number 13 that starts with the element boron is called the boron group. Group number 14, which starts with carbon, is called the carbon group. 15 starts with nitrogen, the nitrogen group. I think you can do this one. The group number 16 is called, the modern name is called the oxygen group or the oxygen family. An older term, if you find an old textbook, you may see them called the chalcogens. Those are two names. And so I reference this because several books will call them chalcogens. Then there are not groups that go up and down, but blocks that we need to know. The middle are called the transition metals. If there were teenagers on the periodic table, right there, they don't want to behave and follow the rules. Okay? They're a group that are very important to us that include iron and cobalt and nickel and copper and silver and gold. So they're very important to us, but they behave a little bit weird. It's because of where the electrons, how they are distributed there. And then in the bottom two rows are called the lanthanide series and the actinide series. The lanthanide series are called the rare earth elements. You can probably tell there's just a few of them around the Earth. The actinides, almost all of them are man-made. All right. Each family tends to have a characteristic. And so the halogens are a group that's called, that's group number 17 up there. It starts with fluorine. Okay. They can be described in two ways, as being highly active. Another way to say that is that they're highly reactive. Okay. They really like to react with stuff. At room temperatures, two of them are gases. Fluorine is a pale yellow gas. It is the most reactive element on the periodic table. Chlorine is a greenish yellow gas, and we already tried to breathe in chlorine. Bromine is a reddish brown liquid, and then the last one is a radioactive solid. What's interesting about some of these is that most elements are found by themselves, just one atom by themselves uniquely. Most of these are what are called diatomic. If you find them in nature, two of them are linked together as the element. They tend to react with hydrogen, that number one element, to form acids. Fluorine is a really reactive element, and it loves to make a reaction with calcium. We don't have any fluorine in the building because if fluorine leaked out, it has the property of actually being able to be absorbed and go right through your skin, and it finds calcium, your bone, to react with, and it actually will dissolve the bone inside your hand while you're sitting there watching it. The only treatment is to go and get an injection of extra calcium in there so it reacts with that extra calcium, not your bone. This is not something I allow freshmen to deal with. I don't even let seniors deal with it, and even in grad school, people are very cautious about using that. It's really, really reactive. The alkali metals way on the other end are ones that are used often and found quite often. They're very soft metals that can be, most of them can be cut with butter knives. They tend to react with air and water to form explosive hydrogen gas. They react with lots of energy and they burn. When they react with nonmetals, they tend to form very, very stable compounds, and the compounds that they are called salts. Now we think of salt as being sodium chloride. That is one alkali metal and one nonmetal put together. It's the most common one that we use, but salt for a chemist is any of those two reacting together. So in terms of a chemist knows millions of salts, whereas we kind of commonly call salt only sodium chloride. And for most of these metals, they have a very low melting point. The inert or noble gases are notoriously not reactive. They are found as single elements. All of them that exist that are not man-made are actual gases. Helium is cool because it's lighter than air. Also, if you breathe it in, it's kind of cool. And again, it's non-explosive because it doesn't react with anything. Really, One of the only uses that we have commercially available that we don't use anymore is using them in these right here. What are this? What's this? What do we call those? A neon sign. Okay. Now, we don't use neon signs hardly anymore. We use LEDs because it's a lot less electricity. But a neon sign is a tube filled with gas. And what we do is we allow a lot of electricity to run through it. And the gas doesn't react, but what it does is it absorbs the energy and then it gives off light. True neon, when it's sighted by electricity, glows red. And originally all neon signs were red, but as they mixed in different gases, you can produce different colors. And so neon signs used to be all over the place. Now it's more of an art form than anything. But that's about the use that we have for neon signs, other than making balloons for, little kids. All right. The periodic law. This is where the periodic table comes in. All right. When people started to discover elements, all right, they started getting a collection of these. And this came from the alchemists, moved into the beginnings of chemistry. And we started getting lists of elements. And you can organize lists all sorts of ways. You can organize them by alphabet, alphabetically in a big list. And some people tried that. But this is kind of hard when you had people speaking Russian and English and French and German. And so that didn't work out so well. So what people started to do was, okay, they thought, let's order them in simple to complex. And they did that by organizing them by light ones to heavy ones, because they thought the light ones should be simple, less things in them, and the bigger they get, the more heavy they get, the more complex they are. And that worked okay. And so there were a lot of people. Now, there was a Russian chemist that is credited with creating the modern periodic table. And the story goes this. He was taking all these elements. And when he did this, we didn't have all the elements. Okay, we only had a portion of them. And what he did was he liked the idea about ordering them in complexity. But what he also did was this. He says, okay, when I look at the order, I see a very non-reactive gas, and the next element I have is a very reactive metal that's really soft. Then you have some others, and then all of a sudden he saw a non-reactive gas followed by a very soft metal that was very reactive. He went, He said there was a repeating pattern or a periodic nature in the periodic table. So what he did was, he did order them in terms of complexity, but he grouped everything that reacted the same. And when he did that, he created all the families. And so the non-reactive gases were all the noble gases, and the next group was all the soft metals, the alkali metals. And when he did that, what he realized was that in his collection of elements, there was an extra element, okay, one right here and one right here, but this element didn't line up with the one above it in his list. He actually had little blocks and he would move them around on a desk. The desk is now in a museum and you can look at it. But he said, this one doesn't match the others. But if I move it over one, then this element matches everything above and below in how it reacts. And then he said, there should be an element right here that should have these properties. It should weigh this, it should have this density, it should react this way, it should have this melting point, and he made all sorts of predictions. And then 40 years later, they discover an element, and he was almost exactly right in terms of his predictions of what it should be because of this repeating pattern that he saw. And that's where we get our periodic table today, is the ordering. Now, using weight didn't actually work. There's a couple places. If you take a look at cobalt number 27 and nickel number 28, cobalt weighs 58.9 and nickel weighs 58.7. Do you see the cobalt is heavier than the nickel? And that's because of differences in neutrons. If you now look at the periodic table, it does increase in complexity, but it increases 1, and then 2, then 3, then 4, then 5, then 6, then 7. What are those whole numbers representing? Protons. And so it is an increasing complexity, but it's not weight, it's protons. And we line them up to make sure that everything reacts in groups so that we can extract information. And so that is where we get the periodic. It's a repeating pattern. That's what the periodic table means. It's a British video. It may use colorful language, okay? It's going to describe reactivities. Okay, so what they did was they took all the metals in that group that you can get your hands on. They took lithium, okay? Lithium reacts exactly like all the other metals. When it reacts with water, it creates a gas, hydrogen, and it creates heat. Now lithium reacts a little bit, creates a little bit of bubbles, not a lot of hydrogen, and it creates a little bit of heat, not a lot of heat. When you drop in sodium, more heat is created and more gas is created, and that metal actually creates fire inside of water. Put in potassium, it got dropped in, created more heat, more gas, more fast, and it exploded. And then you saw what happened with rubidium and cesium. And so metals tend to have this reactivity. As they go down, they get more reactive, and as they go across, so here, as they go across and down, they get more reactive, and you can see the most reactive is the one at the bottom of the chart in that corner. Now, nonmetals are exact opposites, right? And so if metals get more reactive going down, nonmetals get more reactive going up and going in the opposite direction to fluorine as the most reactive nonmetal. Now, there's this group right here. They're nonmetals, but in terms of reactivity, what is special about this group right here? They're the what? Which group? The noble gases, which don't react at all. And so they fall out of that trend. And so we have reactivities based upon whether it's a metal or a nonmetal, and they're backwards depending upon what they are in terms of strength of reaction or how reactive they are.